Okay, good afternoon. So today we'll hopefully finish up the synchronization and start talking about multi-threaded kernels. So what we were talking about was deadlock. So let's continue from deadlocks. We made a definition of what deadlock is. We talked about necessary conditions, required conditions for deadlock to happen. And now let's continue from where we left off in the last lecture. Okay, so we talked about the four conditions. Just to remind everybody, in order for you to have deadlock, it's necessary to have a mutual exclusion when threads access resources. We need to have hold and wait, meaning that users will have to hold the resource that they own and then wait for the resource they want. So if they release the resource and then start waiting, you won't have deadlock. No preemption. This means that if a thread acquires a resource, you cannot take it away unless they release the resource. And finally, circular waiting, meaning that you have threads waiting in a circle for the resources that they want while holding the resources that they own. Now let's get a little bit technical, not much, just a little bit, as much as needed to explain some of the algorithms that are going to come. So let's talk about first resource allocation graph. So what is this? So I'm going to just define some symbols. We're going to talk about threads as a unit of computation here. We're going to talk about resources, and each resource is going to have some units. So for example, you might have, a processor with 4 CPUs. Then you have 4 units of computation. You might, if, for example, the unit of allocation of memory capacity is a page, then a memory with some number of pages would be one resource with some number of units. So so these circles inside each resource shows so they show how many units of this resource we have available. Now, right, so that's that. Now we're going to assume that users interact through 3 main functions. So they request a thread, they request a resource, they use the resource, we don't care how they use it, and then finally they release the resource. So these are the interactions of threads with our abstract system. Now, given this, we can actually construct a resource allocation graph. So this is going to be, we're going to put a vertex. We're talking about a graph. So each vertex could be a thread or could be a resource. And an edge between 2 vertices, if one end is a thread and the other end is a resource, that indicates a request from that thread to that resource. And if the edge goes from a resource to a thread, that indicates that the thread owns that resource. So an outgoing edge from a thread means a request. An incoming edge to a thread indicates basically possession. Now let's look at an example. So this is one example. I have 3 threads and 4 different resources. Resource 1 and 2 have 1 unit. Just just for this one example, let's look at edges. So this edge means that this one means that T1 requires R1, and this edge means that T2 owns R1 or has already acquired R1. This means that these two units of R4 are not yet allocated, and one of them is allocated to T3. Okay, so hopefully that's kind of clear. Now this is an example where deadlock exists. So I'm just going to show you the deadlock. We're not going to, analyze it or anything, but let's see if we can construct the dependencies, right? So where you have the deadlock is basically you can start from here and construct this loop of dependencies. So in this case, T3 wants resource R3, which is owned by T1 and T2, and T2 needs a resource that is owned by T3. So in this case, we have a deadlock because we have this loop. There's this circular waiting. So basically, T3 is waiting for T1 and T2, either one of them, but then T1 is waiting for T2 to finish. So T1 is not going to finish, and then T2 is waiting for T3 to finish to get resource 2. So everybody is waiting for everyone, and this is going to be a deadlock. So this is another example where there is a circle of dependencies, but we don't have a deadlock. So this is the circle of dependency, if you wish, right? So this is not going to end in a deadlock situation, because it could well be the case that T2 finishes and this resource becomes available for T1, and then T1 finishes and this resource becomes available for T3, and T4 could also finish. So this one doesn't have a deadlock, this one does have a deadlock, and this is just a simple example. Now, one thing to note is that it's not always the case that you know beforehand what resources your thread is going to need. For example, you might have a database with hundreds of tables, and we could imagine each table being a resource that your thread might want to access. And it would depend on the input to identify which table your thread needs to access. It could be that for one particular query, your thread is going to need 5 or 10 tables, and for another inquiry, your thread might only need 1 table. So you don't know beforehand, and it could actually change over time. So as you can see, for example, T1 at this point in time owns R1, then releases it, and then releases R3, and maybe, like, first of all, you don't even know how many threads there are. That could also be dynamic, so you might have dynamically added vectors to this graph, and also the demands could also dynamically change. So generally speaking, the problem of deadlock is not a static problem. It's usually a dynamic problem because the environment is changing and that makes things a little bit complicated. Now, how can we, handle deadlocks? So the first thing that we can do is to just ignore them and pretend that deadlocks would never happen. After all, deadlocks are rare to happen usually. So you could just say, I'm not going to care about them. So this is usually the case in most of the systems. They don't have a particular deadlock handling mechanism. So most operating systems actually don't deal with deadlocks. But if you end up implementing, real-time or embedded operating systems where meeting deadlines and constraints are of utmost importance, then you cannot use this method of ignoring, because in a general purpose operating system, probably you guys don't remember, but back in then you would have this blue screen in Windows, and you would just restart your system and start over, right? So that would be worst case scenario. But if you're sending a satellite up there and a deadlock happens, then millions and trillions of dollars are wasted. So, okay, so that's first. Yeah, Deadlock Dinner Club. So the second approach that we can take is to allow the system to enter deadlock and then somehow recover from that. Let me pause this. It's gonna go forever. Okay, no, I can't pause it. Okay, so that's the second approach, to let deadlocks happen and then recover from them. For this, we will have to have two components. The first one is deadlock detection. We need a mechanism that could detect that a deadlock or deadlocks have happened. And we also need a deadlock recovery mechanism. Once we detect, how can we recover? So we're going to talk about these two next. Now, there is a third approach, which is more conservative, and it says make sure that deadlocks never happen in your system. So for this one, we kind of need a monitoring mechanism that could ensure that answering or responding to a request does not lead to deadlock. So we'll talk about this as well. So what we're going to see next is we're going to talk about deadlock detection, then we'll talk about deadlock recovery, and finally we'll cover this deadlock prevention. I should have mentioned it actually. So this one is deadlock. There is no hyphen. Deadlock prevention methods. Okay. So let's start with deadlock detection. I'm going to assume for this algorithm that there are m different resources, and there are n threads. Now, we're going to say that the capacity of resource I is Ci. So here I show you a vector of m elements because we have m different resources, and each one of them has a capacity. This is how many units of that resource we have. Then we also maintain a vector of free units per resource. So this shows us how many resources per type are currently not allocated and they're free and we can use them. So that's free resources, F. Then we're going to have a matrix of resource allocations. So each row is going to represent a thread. That's why we have n rows. And each column is going to represent a resource. Now, Aij shows the allocation of resource j to thread I. How many units of resource j have been allocated to thread I. And then finally, we also want to have a notion of requests. This is another matrix. This shows, again, each row represents threads, each column represents resource types, and Rij represents the resource request of thread I for resource j. Now, what you can actually write for this as a mathematical equation is for each j, for all j, pick any resource type, then the capacity of that resource should be equal to the amount of free units, how much free units we have, plus the sum of allocated units. So the sum of Aij, sum over I, shows you how many units of resource j has been allocated already, plus how much is free, and this should be equal to the capacity of resource j. Now, why do we need all of this? So here comes an algorithm to detect deadlock, if deadlock has happened. Now, this algorithm assumes that we have all those requirements. So it assumes that threads wait while holding resources. It assumes that threads only release resources when they want, so they can't be preempted. This also assumes that resources, each single unit of resource can be only owned by one thread. So there's no resource sharing per unit. So each unit goes to a single thread. So these are the assumptions. And this, what it wants to do is to detect if there is a path for completion, if there is a way for the system to terminate. How do we do that? So the way we want to do this is we're going to look at the vector of free resources. Now we pick so we pick each thread, and then we look at the request of this thread. And we see if we have enough resources to give all the requests that this thread has. If we do have that many resources, we can say that this thread will finish, right? Because I have enough resources to give to this thread. So this thread is going to finish eventually. So I can safely remove this thread from my list because it's going to finish eventually, and assume that it's going to release all the resources that it has. So this vector A shows all the resources that a thread I currently has. Now that I made sure that this thread can finish because I have enough resources that this thread wants, I can assume that eventually it will finish and it will release all its resources. So I add the allocation, its current allocation, to my free resources. And then I continue. I pick another thread. I check to see if this thread could also finish. And I just iterate this until I cannot find any thread that can finish. So if I find a situation that there are threads and they have requests that are more than my available resources, and this is correct for all of them. So all the threads that I have, none of them can finish because all of them have requests that are more than my available resources. Then I have a deadlock. So this is a deadlock detection algorithm. It's pretty simple, right? Now, let's look at some of the things that I marked here. So yeah, so this if basically looks at threads that can run to completion. So I explained that. This summation here says once this thread finishes, I can just add the currently held resources by this thread to the pool of available resources. And at the end, if this unfinished set is non-empty, meaning that if this algorithm terminates while this unfinished set has a bunch of threads in it, this means that I have deadlock. So I have detected deadlock. Now, you might ask, okay, when should we run this algorithm? This algorithm is actually a little bit expensive to run. Now, one option is to run this every time a request is made. So every time that a thread makes a request, you can just run this algorithm to make sure that everything is fine so far. The second one is you can run this every time a request cannot be granted, right? So you don't probably need to run this algorithm every time a request is made. Just wait until a request is made that we cannot satisfy. Now, if a request is made and we cannot satisfy it, it doesn't mean that deadlock has happened, because it could be that I cannot satisfy your request now, but once one of the threads finish, then I will have resources to allocate to you. So it might be a good time to check if this could happen eventually, right? So that's option 2. And then option 3 is just periodically run this to see if deadlock has happened. So without, these two are event-based. So we're waiting for an event, which is a request that is either made or cannot be granted. This one is basically periodic. It's not event-based. So you at certain frequency, you run your algorithm. Okay, so we talked about a deadlock detection. Now, what should we do if we detect deadlock has happened? Now, we have a bunch of options. Let's consider them one by one. So the first one is to pick a victim and force it to give up its resources. So basically, in worst case scenario, send a kill signal to this thread, make it die, and when it dies, all the resources are available. Now, we have to be careful about this option, because sometimes when you prematurely terminate a thread, it might not release the resources that it holds. It might not clean up. So that's one thing. The other thing is that you have to sometimes make sure that this victim, if chosen, killing it would help us get out of the deadlock. You might kill a thread if you randomly choose a thread that killing it might not be helpful to basically break the cycle. Now, if there are no single thread that terminating them could help the system get out of the deadlock, then you can just start terminating one by one until deadlock we can get out of deadlock. So there might not be a single thread that when terminates, the system can get out of deadlock. So in that case, you will have to choose multiple victims. The other thing to note is if you're, for example, writing some, if you have a thread, for example, in a bank situation that is, you know, has locked bunch of databases, a bunch of tables, and it's completing a transaction, right? So it's in the middle of, you know, putting money from, you know, withdrawing money from one account and putting it in another account. And it has acquired some locks. It has locked a bunch of tables, and now it wants to lock another table, but it has already started making some progress. If you kill that thread, you might put your entire system in a inconsistent state because you're prematurely terminating a transaction, which is not safe, right? So this termination might work and might not work depending on the system. So that's first option. So somebody's asking, does the non-empty array in the deadlock algorithm contain the threads in deadlock? Non-empty array contain the, oh, so you mean whatever thread that remains in that unfinished set, are they the ones causing the deadlock? Yes, I believe so. So the threads that remain in that set are the threads that are waiting on each other, right? Because otherwise, if they were not waiting on each other, they could have terminated. So the fact that they stay in the unfinished set indicates that they are dependent on each other. So they're waiting and holding in a circular way. Good question. Okay, so what is the second option? The second option is to proceed without the resource. What does this mean? It basically means putting some extra work on the programmer to think about scenarios where your request cannot be satisfied. So basically, this one is kind of extra work for the programmer. And this actually is a popular option in the systems that you are interacting with them on daily basis. Here is one example. I'm not suggesting that this is exactly for Deadlock recovery, this example of Amazon that I'm going to give, but you will get the idea what I mean by being ready to proceed without the resources that you want. So there are all these studies that Google and Microsoft have published on how much cost they incur if, on average, the requests to their systems are delayed by an extra, let's say, 1 second or extra 10 millisecond or something like that. So they always publish these numbers. You can actually search that. You know, they say if each query takes on average 1 extra second, then we will lose $200 million in revenue or something like that. So it's very important for their systems to work in microsecond scale to finish all the requests as fast as possible. Now, if your request leads to deadlock, then you're gonna lose hundreds of millions of dollars because you're gonna delay a lot of requests. So they absolutely don't want that. Now, one way to do this is to make a request for a resource and have it like sort of non-blocking. If the request is cannot be made, cannot be satisfied, then have a plan B. So it probably has happened to you that you see a post and it has, on Facebook, let's say, it has 100 likes, and then you go like 5 minutes later, it has 5 likes, and then you go 10 minutes later, it has now 200 likes. So the request, when you visited, a request was made to the database to see how many people have liked this post. Or for instance, in Amazon, you go to purchase something and you make the purchase. It says that it's in inventory, but then you receive an email apologizing that, oh, there was a mistake, we didn't have the item. So in these cases, you're making a request to the database, and the database maybe is backlogged, or maybe there's a deadlock, whatever it is, your request cannot go, so you don't get a response back. But then the handler of the request doesn't wait for that, so it just makes an assumption so that the system can continue. And then once you get to know what the real number was, then you can make corrections. So that's another approach, very, very common in commercial systems and distributed systems. So that's another one. It's kind of like a backdoor. It's really not a recovery, but it's kind of like, avoiding deadlock to impact your system. Now, the third option is to have a mechanism to roll back your threads. So your thread is now, instead, like, compare this one with the first option, which we terminated the thread. So this one is a milder approach. It's not that like a hammer getting to the thread to terminate. This one basically says, let me make checkpoints as my thread progresses. And if I find my system in deadlock, then I can just go back to a checkpoint that I made before where there was no deadlock and hope that deadlock doesn't happen. Now, this approach has cost, because you will need to have a mechanism to checkpoint your threads, basically saving the state of your thread and have a mechanism to go back to those checkpoints and pretend to start from there. The other difficulty with this approach is that there's no guarantee that the deadlock doesn't happen again, right? So if you go back to a checkpoint and it's deterministic, the way the threads are asking for resources, you might again end up finding yourself in a deadlock. Okay, so I think the gist of it is that the recovery from deadlock is hard, and that is a segue to the next topic. Okay, so if recovery is hard, so maybe we should just prevent deadlocks from happening. Now, in order for you to prevent deadlocks from happening, you could just go and break the assumptions or those requirements for deadlock that we had, basically mutual exclusion, if you remember, hold and wait. What else did we have? Circular waiting, and what was the fourth one? Come on, my memory. It doesn't matter. So break any of those 4 and you should be fine. So for example, for the mutual exclusion, is fine, but if you have infinite number of resources, then there would be no waiting at all. So you have enough resources to give everybody. Nobody needs to wait. So that's one approach. You, if possible, have infinite number of resources, or have more than the maximum request of everybody combined, and you should be fine. Then deadlock will never happen in your system. The other thing is, don't make threads have requests for the same resource. So make them isolated so that, you know, it's kind of like the example that we saw with communicating threads with, where you would put each thread in charge of a single resource. That way there is no sharing. So threads are not going to make requests for the same resource. And as such, there would be no deadlock. And finally, do not allow your threads to wait. So basically, if they request a thread, request a resource, and they cannot get it, then they should just continue without waiting some other way. It's very similar to that method that we mentioned about deadlock recovery. It's similar. So for example, with phone companies, if you call someone and they're busy, you don't wait for them, right? It just tells you that this phone is busy, beep, 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 bye-bye. Now you can try again. You're not going to wait on the line and waste resources. So you can actually try again some other time. The same with Ethernet, right? If the network gets congested, then all the packets are dropped, and then the protocols and nodes in the network have to retry. So they don't wait. So this prevents deadlock by just avoiding waiting. And it might be kind of inefficient in some cases because it might require a lot of retry. You know, in the case of phone companies, like you have to just keep calling until the phone is available and it's out of the busiest state. So that's another thing to note. The other approach that we can make is we can make threads to ask for all the resources that they want at the beginning, and then they either get all those resources or they don't get it. So this is another way of avoiding waiting, right? Because, or making this is probably breaking the wait and hold, because if you ask for all the resources at once, then you're not going to find yourself in a situation where you're holding some resources and waiting for some others, because you have all the resources that you wanted at the beginning. You got all of them, so there should be no waiting anymore, right? Because you have all of them. So you might end up waiting at the beginning before getting any resources. So at that point, you're waiting without holding. So we basically broke wait and hold situation. And once you get the resources that you want, then you're not going to wait anymore. So you can just go and exit. For example, in the dining politicians example, you can say that I'm not going to allow people to just pick one chopstick first or one fork first and then the second fork next. They have to pick them both at the same time. And if you don't have both, then you're not supposed to touch the one, right? And this way you're kind of avoiding or preventing deadlock from happening. Now, this method is kind of plausible, but the downside of it is that you might actually not know in advance what resources you need, right? So you might end up over provisioning for your resources, which is wasteful. So you might end up guessing that I'm going to need this and that table, and end up, you know, having to lock the entire database to start running your thread, because you kind of don't know which tables you're going to end up needing. Now, the other approach, which this one focuses on breaking the cycle, is to have a fixed order of requests in your system. And by doing this, you're kind of preventing that cycle from happening. Here is an example. So you could potentially put numbers on the forks or chopsticks from 1 to 5, right? In that example where we had 5 politicians and 5 forks, I can put number 1, 2, 3, 4, 5 on each fork, and then force everyone to pick the fork with the lower number. So let's say, let's say I have fork number 1, fork number 2, number 3, number 4, and number 5. So each person has to pick the fork with lower number. Now, if I do this, this person wants to pick this fork, but this person also wants to pick this fork first. It's not going to pick fork 2, because previously everybody was picking the fork on their left hand or right hand, but now I'm breaking that cycle. Now this guy is going to pick fork number 2, this guy is going to pick fork number 3, this guy is going to pick fork number 5, and now I don't have that cycle of dependencies between them having to wait for each other, right? And by doing this, I'm basically making sure that this guy over here can pick both of these two and finish, and then this guy can pick both of them and finish, and then this guy can pick both of them and finish, and then this guy can pick both of them and finish, and then eventually this guy can pick both of them and finish. Okay, so another example is, let me delete or remove everything here so that we can see this example. I eventually learned how to make this, apparently not. I was bragging that I learned, but yeah, I kind of learned. Let's see. Are you going to disappear by yourself? Nope. Oh, come on. Bragging that I learned, but I haven't, sadly. Okay. Now I want you to disappear, please. Okay, so this is another example. So this example is about the, if you remember the, come on, how does this work? Are you kidding me? How do I make this disappear? Oh, it did. Okay, so this one is about the semaphore example, where you had X and Y, and one thread was doing X.P and then Y.P, and the other thread was doing Y.P and then X.P. So instead, I can make both of them to do X.P and then Y.P. And by doing this, I will avoid ending up in deadlock. So, okay. Now, the last thing I want to talk about in deadlock prevention is somehow a systematic way of implementing. Let's say we can't do any of the above. So here comes an algorithm that we can run. Every time a request is made, we're going to assess if satisfying this request puts us in a trajectory that deadlock could eventually happen. And if so, then we say, no, I am not going to satisfy this request. So you reject requests. Now, for this, let's first define safe state and unsafe state. So what is a safe state? Let's assume that we know what is the maximum number of units per resource that each thread needs. So this is a big assumption. As I mentioned, it might not be true all the time, but let's assume that we know this number. So there is a maximum number of resources that I need, that I know this thread is capable of asking. It's not necessarily the number that it's going to ask at any given time, but this is the max that it will need. A safe state is a state where there is a sequence of threads that could run without ending up having a deadlock. So I can, there is a possibility that thread 1 finishes first, thread 4 finishes next, and then 2 and 3 finish, and then I go to 5. So if there is an order where everybody can finish, then I'm in a safe state. If, however, this is not the case, so there is no possible order that everybody could finish, then it's an unsafe state. Now, when I say could finish, it's with respect to their maximum demand, right? So because I don't exactly know how much resources each thread is going to ask in future, I'm going to assume that they're going to ask for the maximum number of resources. And then with that in mind, I will try to find a sequence that even if they ask for their max, the deadlock will not happen. And if I have that, then I'm guaranteed to be safe because they're always going to ask less than their max. And I have already guaranteed that even if they ask for their max, I can finish executing all of them without ending up in a deadlock. So this should actually bring that algorithm that we had for deadlock detection in your mind. With that deadlock detection, we had this, matrix of allocation and the matrix of requests, right? And then we could detect if there is a sequence of threads finishing. Now, if we just substitute that request matrix with this maximum request matrix and run the same algorithm, then we can rest assured that there is a way that, if the algorithm finishes and nobody is in that unfinished set, then deadlock is not going to happen, even if they ask for their maximum. And otherwise, I'm in an unsafe state. Now, being in unsafe state does not mean that deadlock is guaranteed to happen. I want to emphasize this. Unsafe state means that if they ask for their max, deadlock could happen. But I don't know if they would actually ask for their max. It could well be that they don't ask for their max. So if I were to draw something, it's going to be safe states and unsafe. And let's say this is deadlock. And a thread could be in safe state and come to unsafe state and come back to safe state, go to unsafe state, and then eventually end up in deadlock. So a deadlock is definitely an unsafe, but coming to unsafe state does not mean that deadlock is guaranteed to happen. No, it could well be that we go back to safe because someone terminates without asking their max. Okay. Yeah, so basically unsafe only means deadlock is possible. It doesn't mean that deadlock is guaranteed. Now, here is an example. Let's say that you have 3 threads or 3 processes, A, B, and C. Let's assume that there is only one resource, and this resource has 10 units. So basically, we have 10 units of a single resource. Let's suppose that A already has 3, but the maximum request could be 9. So this is current allocation. This is the maximum A might need. B has already 2. It could ask up to 4. C has 2, and it could ask for up to 7. Now, given that we have 10, now A has 3, B has 2, and C has 2. So right now we have 3 left over, right? So it's 10 minus 7, that's 3. So this is basically our F, 3 resources. We have 3 resources left. Let's see if we are in a safe state or in an unsafe state. So looking at this in a table, I have A that already has 3, B has 2, and C has 2. Now I'm going to show you a sequence that is possible to make sure that everybody will finish, even if they ask for their max. So let's say immediately at this point, everybody asks for their max. Now A is asking for 9, B is asking for 4, and C is asking for 7. Now this means that C wants 5 more, B wants 2 more, and A wants 7 more, right? Now I only have 3, but this 3 is enough to make B finish, right? So I can give what B wants, and then B could finish. Now after B finishes, I will have the resources that B holds now. So that will be added to my pool. So I already had 3. Now B finishes, it gives me back the 2. Now I have 4 free resources. Now I can satisfy C because C wants 5. So I can give C all the 5 that it wants. In this case, now C finishes, and C is going to give away the 2 resources that it holds. And with that, so I have 5 plus 2, that's 7, and that's enough for me to finish A. So I can then give all the resources to A, and A can finish. So this is a safe state, because even if everybody simultaneously asks for their max, there is a schedule, in this case B, then C, then A, to execute them all. Now let's assume that A asks for 1 extra resource. So A has, if you remember, A has 3, B has 2, C has 2. Now let's say A asks for another resource. So we go to this state, right? A now has 4, B has 2, C has 2. Is this a safe state? And the answer is no. Now we're in an unsafe state, because how many resources are we left? We have 2 more resources. If everybody requests for their max immediately after this, so simultaneously everybody asks for their max, so A would want 5 more. Oh, did I make a mistake here? My math is bad. This is 6. Sorry. Yeah. So A wants 5, B wants 2, and C wants 5. Right now, I have 2 free, so I can give it to B. Right. B can finish, and then B releases the 2 he has. Now I have 4. So after this step, I will have 4 resources. A wants 5, C wants 5, and I only have 4. And now I have a deadlock, right? So it's not a safe state. It means that if they simultaneously ask for their max, I will have deadlock. So it's unsafe. Now, given this definition of safe and unsafe, I can now define Banker's algorithm. So this is basically identical to deadlock recovery. The only thing I added is instead of checking for the request and comparing request with F, I'm checking max minus A with available. So this assumes that simultaneously everybody is going to ask for their max. And if they already have A allocations, now this is how much extra resources they might want. And then it's the rest of it is similar to the deadlock detection. And if this terminates with this unfinished set being non-empty, then I'm in trouble. So deadlock could happen. So this Banker's algorithm can say if a state is safe or unsafe, right? Now, what we're going to do with this is to keep our system always in a safe state. That's all. So every time a request is made, we say, if I satisfy this request, do I end up in a safe state or an unsafe state? If satisfying this request puts me in unsafe state, I'm going to reject it. If satisfying this request puts me in a safer state, then I'm going to grant it. So that's how you can actually prevent deadlocks from happening. Now, the reality of this is that, deadlock prevention is hard. And, running this algorithm every time a request is made is just probably not practical. The other thing is that we don't really generally know how much resources each thread could want at the end. So at the end, this whole thing that I just showed you, to be honest with you, is just theoretical analysis of this. In reality, this is too much to do unless you're doing really like mission critical systems that it's of utmost important for you to prevent deadlocks. So again, unless you're doing some sort of very sensitive, very mission critical with hard deadline systems, you're not going to implement any of this. And as I said, right, this is the reality. Most operating systems actually don't care at all about deadlocks. And they kind of assume that it's the programmer's job to avoid them. And if deadlock happens in your program, then you're out of luck, like you didn't do your homework to prevent them from happening. Okay, so we kind of finished this synchronization. So this one was kind of like a detour from operating systems. I mean, at the end of it, we kind of talked about what operating system could do in, facing deadlock. But many of the things that we said also was applicable to programmers and application layer. So it wasn't necessarily operating system stuff. But anyhow, so this synchronization lecture or lectures were kind of like a detour for you guys to get familiar with the concepts of concurrency, and hopefully you got some information. I know that next year, I think you're gonna take CS 326. I think I don't exactly. I think it's 326. I don't know the multi-threading stuff. So hopefully this would help you with that course. which dives deeper into multi-threaded applications, how you can write really efficient multi-threaded applications. But this gives us enough information now to talk about what kernel has to do to support threads and concurrency. So in the next lecture that we're going to start now, we're going to talk about multi-threaded operating systems, how we can implement multi-threading. Okay. Okay, so let's get started. It seems like that nobody has any questions. What are we going to see? So in series of lectures that are going to come starting from today, we're going to see how we can implement threads. In particular, how can we create threads? How can we implement yield, switch? I know that you've already started doing this in your labs, but nevertheless, we're going to talk about it. Once we're done with that, we'll start talking about kernel versus user managed threads. And once we're done with these two topics, I start talking about how we can implement these synchronization objects. The objects that we learned how to use, mutex, semaphore, and monitor. How can we go and implement them in operating systems? Okay. So let's start with the kernel managed multi-threading. So this is the big picture that we're going to talk about. So this is our end goal, is to have a system that can support something like this. So what is this? So in this system, I have kernel threads. So these are the threads that run in kernel mode, but they're threads. So each one of them has a TCB, each one of them has a stack, but these are in kernel space and they run in kernel mode. So I'm calling them kernel threads. My system is capable also of running user processes. So these are the code that run in user space. So inside kernel, for each process, I'm going to have a PCB. And inside each process, I'm going to run multiple threads. So I'm going to have threads. So I'm going to run threads. So what do I want for each thread? So I need a TCB for each thread inside my kernel. And if you can remember from the 2-stack model, I'm going to have a single kernel stack for each thread that I create. So why is it called kernel managed multi-threading? This is because for each user level thread, I have a TCB. So it's supported by the operating system. Now, if I want to context switch between my threads, it's going to be done through operating system. So operating system makes a scheduling decision to run the threads. So who gets to run is operating system's decision. If a user thread requests I/O, for example, operating system puts that thread into sleep. So different threads are kind of independent because each one of them has a TCB from the operating system's point of view. So we're not going to, for example, if one thread asks for I/O, we're not going to block all the other threads because they're independent. So one thread goes to waiting, the other thread could be running, right? So they're independent. The kernel is managing them for us. So basically, there is this one-to-one relationship between user threads and kernel TCPs. And now, once we're done with this, then we'll talk about user managed threads, where you would have a 1-to-m or 1-to-n relationship. So from kernel's point of view, you will have only one TCP, but then inside the user space, you could have n threads, and they're managed by the user program. So user program schedules them, takes care of them. And one thing that we will see is if one of them asks for I/O, all of them get blocked because from the operating system's point of view, it just looks at all of them as one thread because it has only one TCP for them. So if one of them is running, operating system has no idea how many others exist. So from the operating system's point of view, this is just one thread. And if this one thread is asking for I/O, I'm going to put it to sleep. So the entire set of threads could go to sleep. So we'll talk about that when we're done with this kernel managed multi-threading. So just to recall, we talked about different states of your thread. So when you create a thread, while it's being created, it's in an once state. Once it's ready, it's going to become ready. Then it gets scheduled. The state changes to running. If it waits for something, IO, lock, mutex, semaphore, condition variable, whatever, it's going to change the state to waiting. Once it's done, once it receives the signal, or once the threads that you're waiting for exit, then your state is going to change back to ready. Eventually, you're going to run again, and at some point, you're going to terminate and finish. So that's basically the life cycle of threads. And this is true for both kernel threads and user threads. Now, one question is, how do you context switch, or what triggers context switching between threads? How do you, going back, what makes threads to go from running to ready and another thread from ready to running? What is this? How is this triggered? Or from running to waiting, how is this triggered? So the first one is a synchronous event. So a context switch could be triggered synchronously with respect to the program. And this means that if you call a system call, or if your code executes a wrong code, like if you divide by 0. So these are synchronous events caused by your program. So let's say you call read from a file, and the operating system has to go to the SSD to bring the data that you wanted. So at this point, the operating system could make a decision to suspend you and run another thread. Or if you call yield, for example, then you call kind of like a system call is called when you call yield, and operating system may make a decision to suspend you and start running someone else. It could be that the operating system decides to run you again, right? Not context switch. So calling yield does not necessarily mean a context switch is guaranteed. For example, in your system, if you have one high priority system and a high priority task, and the rest of them are low priority, and a high priority calls yield, you don't want to go and run the low priority ones. You want to continue running the high priority until it finishes. So here's an example, right? So let's say we have this function compute pi, and in a while loop, we compute the next digit, and then we call yield. So every time we call yield, the operating system could just context switch to someone else and at some point come back to us. Now, the other source of context switch could be asynchronous events, such as interrupts. Now, for example, a timer interrupt could go off and lead to a context switch. Or, it might be that the read request that you issued to SSD has been brought to memory, and now the SSD will raise an interrupt. And once the interrupt is received, maybe the operating system preempts the currently running thread and goes back to the thread that asked for this IO, the one that called read. So it could lead to a context switch. Now, how does a system call handler or an interrupt handler or an exception handler, how do they look like? So here I'm not talking about a specific handler. I'm just talking about generally how they look. So generally, at the beginning of your handlers, so if you look at different operating system codes, and I think this is correct for your labs as well. If you look at the first lines of your handlers, either interrupt handlers or system call handlers, you will see that we're pushing a bunch of registers on the kernel stack. The reason for this is in your interrupt handler, you're going to use some registers, right, to handle the interrupt. You might want to do some computation. You might need some of those registers. Now, if you remember, we had to have this transparent mode switch, meaning that we needed to kind of save the state of the running thread while before we start handling the interrupt. And once we're done, we want to go back to that state. Now, the registers might contain what the user program was doing, right? Maybe the user program was adding a bunch of registers and doing some multiplications and some subtractions and some additions. So one thing that you have to do at the beginning of your interrupt handler is to save the registers that you are going to change. Now, in some systems, you might have convention saying that interrupt handler or system call handler is only supposed to touch or modify certain registers, and it's not going to modify any other register. So if that's the case, then you can just save those registers that the interrupt handler is going to modify potentially. Now, if you don't want to have this convention to restrict yourself to certain registers, then you could just save all registers, and that way you're free to use any registers. Now, these two, there's a cost, right? Saving registers on kernel stack means going to memory. So you're gonna read from your registers and then write them in memory because the stack is on memory. And going to memory is expensive. So saving all registers for a system that has tens of registers is going to be expensive. But it's easier because then your hands are not tied to a certain number of registers. You could use any register you want to do your handling. Alternatively, you could just go with the convention of, setting some convention and saying that in my system that I'm designing, I'm going to only touch register 1, 2, and 3, and that's it. This will make it easier for the saving, because now you only need to save only 3 registers, because these are the 3 registers that you're going to change. But it kind of like restricts you to only using these 3 registers for all the kernel tasks that you might have, for all the handling, for your device driver, for all of that. You're constrained to using these 3 registers. So it's a cost benefit. Now, whatever you do, either saving all registers or saving only few registers that you need, at the end of interrupt handler, once you're done with handling the event, you're going to pop them from the kernel, right? You're going to pop those registers, either all of them or those few, and then you're going to return. Now, one note about this return is that this return will depend on what mode you want to return to. If you came here from a user mode, from user to kernel, now you're going to go from kernel to user. If you came here from a kernel code, you're going to this is going to be a simple return function, right? Simple function return. So depending on the mode that you were previously at, this return depends on that, right? Okay. Now, let's say that you want to switch between 2 threads. So you're running thread A. Now you want to context switch to thread B. What should you do? So I'm going to write this function called thread switch. It has 2 inputs, old TCB and new TCB. So old TCB is the TCB that I was running the system under. And this new TCB is the TCB that I want to start running. I guess I am going to end this lecture here because starting this is not going to be fun, because it's going to take some time actually explaining this function. So maybe I end today's lecture earlier than always. It's okay to have an exception, not always go over time. So I'm going to end this lecture here because, again, as I said, explaining this slide is going to take a little bit of time, and I don't want to end in between. So I think it's a good idea to pause here. Now, thank you for sticking around and coming to the lectures. And thank you for those of you who are watching these lectures, or this particular one in recording. So take care, be safe. Talk to you later. Bye-bye.